So our next goal is going to be to see that in a CW complex, higher homotopy groups determine to some extent the CW complex. So we'll see the simplest case of this. If they all vanish, then the CW complex is contractible. I don't mean all higher, all homotopy groups vanish. But before we see that, we'll see two preliminary things which will be put together essentially to give that result. Firstly, we'll see products of CW complexes as CW complexes. Okay, so suppose X and Y are CW complexes, and cells indexed, they were index sets by AN, the collection AN and N in greater than or equal to 0, and BM, let's say, M greater than or equal to 0. Okay, then so we can call it a theorem. This is quite easy, that X product is a CW complex with cells indexed by, well, or rather, instead of saying that, with n cells corresponding to the union, whether you can even say disjoint union of, I look at all k plus l equals n, and k and l are greater than or equal to 0, and I look at AK cross BM. So I'm looking at, for example, the 2 cells here are the 0 cells here and the 2 cells here, the 1 cells in both cases, 2 cells and 0 cells. Okay. All this is really just simply based on the fact that dk cross dl is equal, by here I mean homeomorphic, to dk plus l. Okay, so hence we get these. Okay, so we define cell structure using the attaching maps. So what I want to do using the attaching maps, so phi, so suppose, let's set up the what notations do we have. So suppose we have an n cell. Okay, so that means that suppose alpha belongs to AK and beta belongs to BL, and k plus l is n. We are going to attach an n cell. Okay, so we want to define phi. Let's call it phi alpha beta. So it's pairs which form n cells, even the pair alpha beta. This is going to map boundary of dk cross dl, which is dn. Okay, it will have to map it to the n minus 1 skeleton of x cross y. And note, we are attaching cells inductively, so anything which is in the n minus 1 skeleton of y or x will already be here. So more formally, we'll have to inductively prove a couple of statements together. So let's see what this map is. So this is going to be equal to boundary of dk cross dl union the dk cross boundary of dl. Okay, this is simply the square has, or a cube has, a vertical boundary as well as a horizontal boundary. So you have two kinds of boundary components which are here. So we define this by, well, then that's kind of clear what you would have to do, right? So here we will define phi alpha beta for, so if I take x in boundary dk and y in dl, well, then this is going to be just on this guy we have a boundary map, phi alpha of x. Okay, and I take the pair which identifies it with the map which is going to be just y itself. Okay. So this is going to be contained in x n minus 1, and sorry, not n minus 1, k minus 1. This is going to be in YL. Okay, and this product, hence it's a pair, the product belongs inductively in the n minus 1 skeleton x cross y of n minus 1, and similarly phi alpha beta, if I this time have x in dk and y in boundary DL, okay, then we just take x itself and then we take phi beta of y. Okay, this again belongs to x cross y, the n minus 1 skeleton. There is of course one verification to do, which is verify that if x, y is in both boundaries, okay, so this belongs to boundary dk cross boundary dl, then I can apply either map, I should get the same result, right? So then what happens is that phi alpha beta of xy is equal to, let's apply the first definition, phi alpha of x comma y, but this is equal in the quotient. So remember, y is now going to be in boundary of DL, and any point in the boundary is identified by using its gluing map. Okay, so it's going to be phi alpha of x and phi beta of y. This is because we are taking a product space, and this is the quotient identification when we are gluing CW complexes. And so this is going to be the same thing as x by the same argument, phi beta of y. So we can reverse the two and we get this product structure. Okay, so there are a couple of other routine verifications to make, but I will skip those. What we see is that if I take two CW complexes, their product is also a CW complex. Okay, so this is going to be our first step. Next we will look at subcomplexes and extension problems, and then the main result will just follow straight away. So what would we talk about as subcomplexes? Again, more or less obvious. So if I have A contained in X, so this is consists of cells in X, not part of an X, cells in X. And if a cell is in X, give it some name. So cell corresponding to alpha, alpha in AN is in A, and here is the index set, then every cell intersecting the boundary phi alpha of boundary of Bn is in A. Okay. So this is the way in which we can actually weaken this a little, but it's a CW complex with an inclusion map, which is going to be cellular, which takes cells of any dimension to cells of even the same dimension. Okay, so we'll formally define a cellular map later. So it's a collection of cells. So we have the extension problem. So extension problem here is that, so we are given f from A to Y. Okay, want to extend to capital F from X to Y. Okay, so enough to define on cells not in A and inductively on dimension. Okay, so that is, formally we extend to A union X0, A union X1, A union X2, etc. Not union, just comma. And then if we have infinitely many cells, we take the direct limit. Okay, and each one is A union. So you can think of A as A union x minus 1, where x minus 1 is the empty space. Okay, so I wanted to make a uniform statement. So A union xn is obtained from A union xn minus 1, yeah, by gluing or attaching n cells, and let's say along some cells along phi alpha, alpha in some index set, let's call it Bn. Okay, it's indices that are not in A, so I'm giving it a different name. So what does this get us? It gets us something very easily, and then much more to come. So we are going to frequently have this situation. We want to define maps on CW complexes. That's the power. We can define them inductively on cells. Okay. So specifically, if pi n of y is trivial, let me say trivial because some are abelian and some are not, for n greater than or equal to 0. So n equals 0 means path connected. It's path connected. N equals 1 means simply connected. So there it was just a set. So let me actually be a little more precise here, because there are two possible meanings for pi n of 0 being trivial. Do I mean it to be empty set or a single point? So if pi n of this is pi n of a single point set. Okay, so let's assume that it's path connected for n greater than or equal to 0. Okay, then any map f from A to x extends to capital F from x to y. Oh, sorry, not A to x, it's A to y. And the proof is simply we have to extend it on the cells, right? So A union xn is going to be A union xn minus 1 disjoint union of the cells d alpha n, alpha in what I called Bn, divided by equivalence. Okay, define f restricted to d alpha n. Well, how do I define this? Well, I want to define this with a condition. It has to be consistent with the equivalence relation. Okay, and the equivalence relation is only on the boundary. Okay, so I can say before this, on boundary d alpha n, we need f restricted to boundary d alpha n is going to be what? So any boundary point is identified by phi. So it's going to be equal to f composed with phi. So this is f restricted to A union xn minus 1 composed with phi alpha. Let me write that a little more clearly and say that a little more clearly. So let us assume that it has already been defined here. Okay, assume defined here. To start with, this is just A. Okay, and on boundary d alpha n, so if I take any boundary in d alpha n, then if I look at f restricted to the boundary of d alpha n, so that is given by the following point. So let's take a point x here. Then that point x is glued by phi alpha of x. So this point is going to be in A union xn minus 1. Okay, so there we have already got f restricted to A union xn minus 1. So on the n minus 1 skeleton, we have already defined these. Sorry, that's not legible, but you heard me say A union xn minus 1. We have previously defined this. So on the boundary, this is defined. Define f restricted to dn by extending map from Sn minus 1 to Dn. And why can we do this? Because we know all higher homotopy groups are trivial. We saw that, right? When we are all higher, well, for pi 0, this comes from path connectedness. For pi 1, we saw this, and we saw this for pi n for n greater than or equal to 2. So we can always extend a map from a circle to a disk if higher homotopy groups vanish. Okay, so higher homotopy groups vanishing tells you you can always solve if all homotopy groups vanishing, lower and higher, starting with 0, tell you that you can always solve extension problems. Okay, provided you have domains being CW complexes. A particular application of that we will see soon. This itself is important. Usually our target will also be a CW complex, and that is to show CW complexes are contractible if higher homotopy groups vanish. So let's show that. So theorem. So suppose we have X CW complex, and pi n of X, let me write it correctly from the beginning. This is pi n of star for all n greater than or equal to 0. Okay, so not the empty set for pi 0, but a single point for pi 0. So it has a single component. It's not empty. It's path connected though. It's simply connected, and all higher homotopy groups vanish. I'm writing it this way, being aware that pi 0 is only a set. It's not a group. Pi 1 is a non-abelian group, and pi 2 onwards are abelian groups. Okay, but nevertheless, equality makes sense in all cases. So this is pi n of group is pi n of star, equals in the sense of isomorphism. Okay, then X is contractible. Okay, so let's define it map. So define H from X cross 0, 1 to X. Okay, so extending. So we can think of constructing a contraction or a homotopy as an extension problem. So I have not yet picked, so let's pick x0 in X in the 0 skeleton. There have to be vertices, otherwise it will be empty. Okay, and we will extend the map in the following way. So we'll take A is going to be, of course, the base X cross and the top union x0 cross 0, 1, and define H restricted to A is going to be as follows: of X comma 0 is going to be the point X itself. H restricted to A of X comma 1 is going to be the point x0, and H restricted to A at the point x0 and any t is going to be x0. So this defines all the cases, and they are consistent, so they are closed sets. So gluing lemma, we have these things, and by the previous theorem this extends to give contraction H. Okay, as I've mentioned before, it's very useful at times to think of homotopies as simply maps instead of thinking of t as time or anything else like that. So this is just a special case of an extension problem. So if the target is contractible, then we saw that for a base CW complex we can extend everything. In particular, we can take X itself as a target. Sorry, I didn't say target. I said target is contractible. We don't need that. That's a conclusion in this case. All we need is all homotopy groups vanish. Okay. So here I should add also, and conversely needs this little fact, easy to show, that for a point all homotopy groups vanish. Well, if the way I have stated it here, it doesn't need even that. All it needs is that the groups of a point are the groups of a point. Of course they are. They're just well defined. But pi n of star. So I'll make a remark here, which gives the converse some teeth. Pi n of star is the abelian group 0 for n greater than or equal to 2. Okay, so if it's contractible, all homotopy groups vanish in the sense that pi 0 is a single point and others are the trivial non-abelian group and the trivial abelian groups. So this gives a nice characterization. So CW complexes are contractible if and only if all their higher homotopy groups vanish. Okay, so just a quick view ahead, you notice an immediate corollary of this. Corollary of this is the following with the previous results. If pi n of x, so suppose x is a connected CW complex. Let me just write it clearly because this is important. So if I take x as a connected CW complex and pi n of x, and let's say x0 is a non-empty CW complex, 0 for all n greater than or equal to 2, then the universal cover x tilde is contractible. And conversely, why is this? Because the higher homotopy groups correspond to the higher homotopy groups of x tilde. If it's connected, universal cover is connected. By the way, CW complexes are semi-locally simply connected and locally path connected. So they do have universal covers. So if the universal cover has the same homotopy groups, higher homotopy groups as the space itself. So if the higher homotopy groups of x vanish, then universal cover also has pi 1 vanishing and pi 0 being the same as a point. And so it becomes contractible. And conversely, if it's contractible, then all homotopy groups vanish. Higher homotopy groups vanish. And so X also has higher homotopy groups vanishing. Okay, so these are going to be our Eilenberg-MacLane spaces. They are going to be quite extremely important because we are going to look at Whitehead theory exactly in these contexts.